Hi friends, good afternoon. Afternoon is indeed for lying down. This atmosphere is suitable for watching quite complicated physics videos. You can read this question for a while. Although there is a short illustration, there is no harm in watching this short animation. The following system consists of a board connected to a spring attached to the wall. It looks like the contact surface between the board and the floor is smooth. However, the top surface of the board is rough. There is a solid cylinder there. This is roughly the three-dimensional view of this system. Now, the board is slightly deviated to the left, then released. The board will perform simple harmonic motion. What is interesting about this question is that the cylinder rolls without slipping when moving relative to the board. Now, we are asked to calculate the oscillation period of the board. Visually, this is a complicated question. Whatever it is, let's discuss it. As with other simple harmonic motion questions, we have to draw a diagram of the forces acting on the system. This system consists of three different objects. To make it easier to analyze, we will separate this system into two objects with mass. A board with index 1, and a solid cylinder with index 2. We start from the solid cylinder. The solid cylinder is around the Earth. There is the Earth's gravitational force. The cylinder is in contact with the board. There is also a normal force and two upwards. During rolling, the surface of the cylinder will rub against the surface of the board. The friction force has a direction opposite to the direction of translational motion. It seems that this is the only force acting on the solid cylinder. For the board, there is no single force. The force appears as an action-reaction pair. On the board will work the friction force Fs, and N2 in the opposite direction. As an interaction with the Earth, the board also works the gravitational force M1g. An interaction with the floor surface, there is a normal force N1. The stretched spring will exert a spring force Kx1. Before analyzing these forces, we will review the special requirements in this problem. The cylinder rolls without slipping. We can draw some points on the surface of the cylinder and on the board. The cylinder will not slip when each point is in line with each other. This is correct. How to formulate this mathematically? Suppose the board is accelerating to the right with an acceleration of a1 to the right. The cylinder is rotating with an angular acceleration of alpha2. Since the cylinder is rolling, there are two accelerations at the point of contact. A translational acceleration of a2 to the left, and a tangential acceleration of alpha2r to the right. a1 and a2 are the accelerations measured by an observer on the floor surface. In order for each point displacement on the two surfaces to correspond to each other, a1 must be equal to minus a2 plus alpha2r. This is equation 1. All of these forces will interact to form a resultant force. The resultant horizontal force on the board, minus Fs minus Kx1, is equal to m1a1. This is equation 2. The resultant horizontal force on the cylinder, Fs, is equal to minus m2a2, because the direction of a2 is to the left. The resultant torque on the rotation of the cylinder, FSR is equal to half m2r squared alpha 2, because the moment of inertia of a solid cylinder is half mr squared. Let's call these two as equation 3 and equation 4. We have 4 equations, with 4 unknown quantities: A1, A2, Fs, and alpha 2. It seems that these mathematical equations are enough. The next step only requires mathematical skills. We can write equation 1 as alpha 2r equals A1 plus A2. The equation that contains the value of alpha is equation 4. We can write equation 4 like this. We can cross out the quantity r on both sides. From here, Fs is equal to half m2 multiplied by A1 plus A2. In equation 3, the magnitude of Fs is seen. What if we substitute the value of Fs from equation 4 into equation 3? We can cross out m2. Next, arrange the physical quantities based on similar physical quantities. From here, A2 is equal to minus 1/3 A1. Knowing the value of A2, we can calculate the friction force as a function of A1. Why? Because what is requested is the period of oscillation of the board. The acceleration that is identical to the board is A1. So we will substitute the acceleration of A2 into the friction force equation. From here, Fs is equal to 1/3 m2A1. Now, we can use this value of Fs into equation 2. We can write equation 2 like this. Are you familiar with this equation? That's right, this equation is identical to the general equation of simple harmonic motion. So, we have to change the equation to fit the general equation. Omega is nothing but the square root of 3k per 3m1 plus m2. If you still remember, omega is 2 pi over big T. This is the equation of the oscillation period from the board. It seems that all the values have been written on the question sheet. Writing in 1 decimal place, T is around 0.7 seconds. How complicated is this question? Happy learning, everyone!